Hi, so today we're going to be talking about this pathway for catecholamine synthesis. The reason I want to talk about it is because I feel it's a very high yield pathway. So let's start. So going from phenylalanine to tyrosine involves the enzyme phenylalanine hydroxylase, the cofactor being tetrahydrobiopterin. I like this cofactor because there's 4 enzymes that it involves, and only 4 that I've come across, and that's your phenylalanine hydroxylase, your tyrosine hydroxylase, which is the next one over here, nitric oxide synthase, as well as tryptophan hydroxylase, which will be used from tryptophan to make eventually serotonin and melatonin. This enzyme here, if it's defective, the phenylalanine hydroxylase, would give you your classical PKU. And that's the kid who has mental retardation, obviously can't handle tyrosine in the diet, so things like aspartame, which is a type of sugar in many soft drinks, can precipitate problems with them. So if they're fed a phenylalanine-free diet, or more so a diet that's supplemented with tyrosine, then they can turn out pretty okay. And these individuals are detected as a child or as a neonate with the Guthrie heel prick test to check if they have that enzyme deficiency. They can also have problems if they have or they can get the non-classical PKU, which is a defect in the dihydropterin reductase. And that's basically the enzyme that's going to be making your tetrahydrobiopterin. So a defect in that would give you non-classical PKU. And watch out for that one, because that type of question always comes up. From tyrosine going from DOPA, we use the enzyme tyrosine hydroxylase. But before we move forward, there's a lot of things that tyrosine is the precursor of. It's used for melanin, that's for skin pigmentation, a defect in tyrosinase, which gives you your albinism. And as well as if you have a defect in tyrosine transporters, that can also give you albinism. And that's referred to as like locus heterogeneity, or genetic heterogeneity, which is basically 2 different genes being mutated, giving you a similar phenotype. Tyrosine is also used for T3 and T4 hormones. That's your thyroxine and your triiodothyronine. 90% in your blood is traveling around as thyroxine, gets converted in peripheral tissues to T3 by the 5' deiodinase, and then that goes to a nuclear receptor and causes transcription, in contrast to a steroid hormone, which would bind to a receptor in the cytosol, and it would just diffuse across the plasma membrane, bind to a receptor in the cytosol, and then go into the nucleus for transcription. For thyroid hormone, you think of the 4 Bs: brain, bone, BMR, and beta-adrenergic, so it directly upregulates beta-1 receptors, hence the tachycardia with individuals who are who have hyperthyroid, increases oxygen consumption, respiration rate, and basically overall basal metabolism is increased. The breakdown of tyrosine is homogentisic acid, eventually going to fumarate, which can be fed into the citric acid cycle. But a defect in homogentisic acid oxidase can lead to a disease called alkaptonuria. These individuals, the main complication is osteoarthritis. Physical features you'll see is blackened sclera, maybe around they can build up in the cartilage of the ear, and they can also get kidney stones. Apparently there's a higher prevalence in Slovakia and Dominican Republic. Wikipedia tells me so. I don't really know why that is, but I find that's interesting. Dopamine going to norepinephrine involves dopamine beta hydroxylase, and unlike some of those other hydroxylases we talked about, which have tryptophan hydroxylase and phenylalanine hydroxylase and tyrosine hydroxylase, which have the tetrahydrobiopterin, this involves vitamin C and copper, which is on this diagram, but copper is also a cofactor of this. So norepinephrine going to epinephrine is kind of the money step here. This is very high yield. First off, this enzyme here, the PNMT, is upregulated by cortisol. Why is this important? Because 80% of adrenal medulla is epinephrine and 20% is norepinephrine. And it kind of makes sense that cortisol is actually going to help promote this pathway. Both of them are sympathetic fight or flight responses, cortisol and epinephrine. So more cortisol upregulating this enzyme here is a good thing. It'll cause more conversion of norepinephrine to epinephrine. And this involves SAM because it's a methylation. Interesting enough, COMT, which is what's used to break down catecholamines, also uses the SAM cycle for metanephrine and norepinephrine. Whereas breakdown of catecholamines, dopamine, and norepinephrine, or dopamine, sorry, and actually some of these other ones can also be broken down by MAO, which is the mitochondrial membrane, the outer mitochondrial membrane. It oxidatively deaminates catecholamines. And there's a MAO A and a MAO B, and you can selectively inhibit MAO B with selegiline, and that's like a Parkinson's drug because MAO-B has a more predilection to break down dopamine. So here's the SAM cycle. Again, a very high yield slide, but I'm just going to say a few points to tie it into what we're talking about with this. So this last step here, this phenylethylamine and methyltransferase using SAM cycle, is what kind of takes place over here. This would be your substrate taking off the methyl group from this SAM. That's the byproduct here. Now this is used for many things. So you can use this to make phosphatidylcholine. You can use it to methylate DNA. You can use it to methylate what we just talked about in the previous step, and we said the breakdown products using COMT for norepinephrine and medinephrine, breakdown products of norepinephrine and epinephrine, which you'd find in the urine of someone with pheochromocytoma, a tumor of the adrenal medulla. There's a few other things I'd like to mention, but we'll save that for another topic. Alright, thank you very much. Have a good day.